So in the last session, we have defined the various thermodynamic potentials and seen how to obtain different thermodynamic potentials from each other by using the mathematical technique of Legendre transformation. And we have seen that each of these potential assumes relevance in different contexts. It helps us to understand whether or not a thermodynamic system has achieved the state of equilibrium. Now, it's time for us to again come back to the discussion of Maxwell's relations, which already have learned in your undergraduate classes. I have learned the 4 different Maxwell's relations which were derived for closed systems where the number of particles remains constant. And it is worth to remember that or understand that Maxwell's relations are actually a large number of varieties exist, and what we have seen in our undergraduate courses were just a part of Maxwell's relations. Each representation, I told you that we can have the energy representation, you can have the entropy representation, or you can have a free energy representation, that is Helmholtz representation, or what the Gibbs free energy representation. From each of these representations, we will be able to obtain such relations, which are all categorized as Maxwell's relations. Okay, so basically, Maxwell's relations are defined as a set of equations in thermodynamics, which are derived from the symmetry of second derivatives and from the basic definition of thermodynamic potentials. So, and why these Maxwell's relations assume importance is that they are extremely useful to relate often hard to measure variables in terms of easily or measurable or accessible ones. Okay, so we have seen that these Maxwell relations form the basis of obtaining new thermodynamic relations, like you have seen the tedious equations that are derived in thermodynamics classes, and also in just obtaining the Clausius-Clapeyron equation, and all those are new relationship connecting thermodynamic variables in different systems. So all these equations can be derived by using Maxwell's relations. Okay, so they interconnect variables. Some variables are very easy to measure and some are hard to measure, and how to connect them from known ones or easily measurable ones to the hard to measure variables, that is usually done by Maxwell relations. Now today in this session we will be just discussing the Maxwell relations for what is known as the open systems. Okay, so for an open system, for the open system, it's not only that T temperature, volume, see the number of particles is also you can see that n is also a variable. So the effect of n when it is variable, that is reflected in the quantity known as mu, chemical potential. It is a chemical potential which decides the flow of particles across 2 phases. So mu becomes relevant. Chemical potential becomes relevant in open systems. That is what you have to always remember. So in the Maxwell relation that we are going to derive just now, you will see that mu also will be playing its own role. It's not a PBST relationship as we have discussed in the last session. Okay, so always remember that every representation can give a set of Maxwell relation. That is another important thing. Okay, so every representation, every thermodynamic representation gives a set of, this is basic thing what you have to understand, set of Maxwell's relations. And never ever think that those 4 derivative equations you have learned in your undergraduate classes was a sole set of Maxwell relations. It's not like that. Okay, what you have seen was only a tip of the iceberg. Okay, and you have got a lot more relations which are known as the general category of Maxwell relations, which connects the second derivatives, okay, or which are obtained from the symmetry of second derivatives. You know that see, the order of differentiation of an analytic function of two variables is irrelevant, okay, by using what is known as the Schwarz theorem. That is a basic mathematical theorem, Schwarz theorem, okay, for analytical functions. So for analytical functions, the order of the differentiation of a function of two variables is irrelevant. So you can just invert, you can change the order of differentiation, right? So based on that fact, we are able to obtain new and new relationships. So let's see how to do that one in a different representation. So as per our book for study, we will be depending on two of the representations. I suggest you to follow the same thing as far as your syllabus is concerned, and always keep in mind that there can be equivalent other formulations as well. So I'm going to first take the Helmholtz representation. Okay, so in Helmholtz representation, you know, by representation we mean which physical quantity we are going to focus on, that's all. In Helmholtz representation, so let's start from the Helmholtz representation. Thereafter we'll discuss the Gibbs representation as well. Okay, the free energy is given by F, Helmholtz free energy, F or A. You know, okay, it was defined as simply U minus Ts by the Legendre transformation of internal energy. You got it. Okay, so let me say that this is my equation number 1 to begin with. So let me take the total differential of the equation 1, means I'm considering the infinitesimal change in the parameter F. So let me say therefore dF, I'm considering the infinitesimal change in the free energy during any process. So automatically to be equal to simply du, okay, du minus TdS. It's quite simple and straightforward, minus S dt. That will be the thing. And now from first law of thermodynamics, I can just substitute for du for an open system. So du is equal to just simply TdS minus PdV plus mu dn. The third term appears because I'm considering what is known as an open system to be general. So minus, so I have substituted for this du here, the whatever quantity is in the bracket, so that is minus TdS minus S dt. So you can just cancel away some of the terms, this minus TdS getting cancelled with the plus TdS over here, and what you're left with is minus S dt minus, I'm putting it in an order, minus PdV, that's all, minus PdV and plus mu dn, plus mu dn. So these are the equations that are remaining. So that is my equation number 2. Right. Now from this one, you can just define the three quantities over here. That is, I can define the quantity S, I can define the quantity just P, and I can define the quantity mu by using this equation in terms of the free energy, Gibbs free energy. That's why it's known as the Helmholtz representation. So therefore, from equation number 2, equation 2 means that I can write S is equal to minus dou F in terms of the free energy, Gibbs free energy, minus dou F by dou T. Okay, so I'm using the first relationship here, dt is there, here on the left side you have got a dF. So I have to make the other two terms, these two terms should be made constant, so that should be 0. For that you make V, the volume, and the number of particles as what? Constant. So automatically dV will be 0 and dN will be 0. The second and the third term in equation number 2 will be vanishing, and you are rearranging it. Okay, so it will be S equal to this one. So let me say that this is one equation. Okay, and similarly I will get two more equations. See, what are the other two equations? What will be getting an equation for this pressure? So automatically same manner you can get pressure P is equal to, there is a negative sign, be careful about it, that's equal to minus dou F with respect to what? This term, minus dou V, dou F by dou V, and you have to keep temperature and number of particles constant, so T and N are constant. So those two terms will be getting 0. And I will get one more equation for mu, the third equation. Okay, the third quantity mu can be also defined in terms of the chemical potential. In terms of the Gibbs the Helmholtz free energy. That is what? That's a positive term. That's dou F with respect to dou N. So you can see that Gibbs free energy. The chemical potential is it can be also expressed in terms of Helmholtz free energy. Okay, previous day we have seen it can be defined in terms of the Gibbs free energy per particle. So it can be even the Helmholtz free energy per particle, but it depends on what all variables you are keeping constant. So I'm keeping temperature and the volume as what constant. So let me say that this is some equation number 3, and we'll refer to as 3a, 3b and 3c. So this is a, this is b, and the last one is what, 3c. Okay, so we can see that now we are writing that is we can say that yes, right, yes, s will be a function of, from equation number a you can see that s will be a function of t, v and en, right? S will be a function, s can be written as a function of t, v, en, okay, because it is related to the free energy through t, v, en. Okay, similarly pressure also will be, it can be also written as a function of t, v, en as the natural variables, and the chemical potential mu also can be written as a function of what, t, v and en through Helmholtz free energy. Okay, so these are the equations of state. If you are able to write entropy, pressure and chemical potential in terms of t, v and n, that will be representing the equation of state in Helmholtz representation. Okay, now let me consider certain quantities. Okay, so s is a function of t, v and en. So let me just consider what is dou s by dou v. What is dou s by dou v? Okay, so I'm going to consider what is dou s by dou v. Therefore dou s by dou v. Okay, and you know s is a function of, remember always that s is a function of t, v and en. So when I take dou s by dou v, I have to keep the other two variables as constant. So I'm keeping, what other things should be kept as constant? T and n should be kept as a constant. So Tn. So what I'm doing, I'm just writing, I'm substituting for s. I'm substituting for s. So what I'm doing is that I'm keeping dou by dou v, that is the derivative, dou by dou v, okay, of, see, I'm going to substitute for this s from the relation A that we obtained. So what is the relation A? S is equal to sorry, S equal to minus dou f by dou t vn, minus dou f by dou t vn, minus dou f by dou t, okay, vn. See that you use the variables along with that one, and this dou by dou v was taken with respect to t and n. So I'm retaining that t and n, okay, along with this v. So whatever I have written at the end is applicable to the first derivative, and whatever I have written, these variables are applicable to the inner derivative. Be careful about that one. Okay, now I told you that we have the property Schwarz theorem, which says that the order of differentiation of an analytic function of two variables is irrelevant. Okay, and the function here is the thermodynamic potential F. So the order of differentiation should be irrelevant. So what I can do is that I can just interchange the order of this derivative. So I'm going to interchange the derivatives. So what I'm doing is that I'm taking this dou by dou t outside. So I'm taking dou by dou t outside. So this dou by dou t with respect to vn, that, okay, no, that will come along with. So that is taken outside. So dou by dou t. Remember, along, okay, whenever you are taking dou by dt, the condition is vn. So that also comes out. Okay, dou by dou t of, see, that negative sign, let me retain itself. So minus, what will be the thing? Dou f by, so, and you take this dou by dou v inside and dou by dou t outside. That's what you know. So minus dou f by, so it becomes dou f by dou v, and see, correspond to this dou by dou v, the variable was tn. So I have to take that tn also inside when you write it. Be careful about that particular important thing. So see, whatever things are kept as constant, that depends on the variable. Okay, so dou by dou v, when you're taking dou by dou v, it is with respect to t and n. Okay, and when you're taking dou by dou t, it is with respect to v and n, that is kept as a constant. So you move it along with. So what I have here is v and n is outside, right? Now let me refer back. Minus dou F by dou V Tn. What is that? So let's go back to equation number C. Yeah, minus B minus dou F by dou V Tn. It's nothing but P, the pressure. P, the pressure. So what you can do is that I can rewrite, I can substitute for this one as P, so it's equal to dou by dou T of pressure. Okay, and see, I can take back this Vn. See, whatever we have taken out, so it's what, dou P by dou T Vn. See that the natural variables are T, Vn. So here also T, V and N are coming, always verified. So you got one of the Maxwell's relations in Helmholtz representation, that is dou S by, I'm writing it in full, dou S by dou V, okay, dou S by dou V, keeping T and N constant, that is equal to dou P by dou T, keeping V and N constant. So that's one of our Maxwell's relations in the Helmholtz free energy representation. So let me say that this is my, okay, you call some equation number 3, whatever it is. Okay, the same manner we are taking another thing. So I'm taking dou S by dou N. So you know that S is a function of N as well. Okay, so I'm taking dou S by dou. Similarly, the same thing we are doing dou S by dou N. Whatever quantities we are interested in, you can take. There are several other ways also, but we restrict to this discussion. When I take dou S by dou N, you know, you have to keep the T and V as constants. So T and V as constants. T and V as constants. So what will be that one? What do you have to do? So you have to write dou by dou N of the same way. You have to substitute for this S. Okay, and what is S? That is, again, here we have already done it. That is S is equal to minus dou F by dou T, that with respect to Vn, and for dou by dou N our variables were T and V, that I'm keeping as outside, right? Now what you do is that you just invert it as we have been doing. So it will be equal to simply dou by, right? So it will be equal to, I'm taking that minus sign outside, so it will be equal to dou by dou T of, what do you have to do? You have to take dou by dou N inside, dou F by dou N. So we use a square bracket still, dou F by dou N, dou F by dou N, keeping T and V constant, right? Then this V and N is coming out. But you know that this dou F by dou N TV, let's look back to ABC. Dou F by dou N TV, see here it is the thing. That is nothing but your mu, the chemical potential. So what we can do is that we can just substitute for that one. So finally you get this is equal to simply minus dou mu by dou T. Dou mu by dou T, that with respect to Vn. And here also you can just check that. So that is our second thing. Dou S by dou N, TV is giving you dou mu by dou T with a negative sign, Vn. So that is 4, equation number 4. The same manner you can get one more relationship. You can get one more relationship in the same manner. So let me just, yeah. So here, what I do next is that, okay, so let me consider dou P by dou N. So actually you could have taken the other one, dou S by dou T, but that doesn't have much relevance because S and T will be coming together. Okay, so what we do is that I'll be taking dou P by dou N, with respect to T and V, because what is my motivation? You have see that the pressure also is a function of TVN. Okay, so I'm considering dou P by dou N. So this relation is what is considered. We can equivalently consider other relations as well. Okay, so it's dou P by dou N with TV, that will be equal to, same manner you can take dou by dou N of, what is P equal to? P equal to, you can see minus dou F by dou V, right? So P equal to minus dou FB minus dou F by dou V Tn. So I'll be substituting for P as minus dou F by dou V, okay, Tn. It's Tvn, which are the natural variables, so we can just say, so it's already with the n, so what is remaining is what? V and T, or T and V, that is remaining there, right? So which we can invert, right? So which we can invert, and I can write, there is a minus sign, I'm taking it outside, so it will be equal to dou, right, dou by dou V, yes, it's taken out, dou by dou V of dou F by dou N, dou F by dou N, and you know what is going to get? Dou F by dou N with respect to what? Tn, dou F by dou N, it should be with respect to TV, right? Dou F by dou N with respect to TV, okay, and then finally you have got with respect to what? T and En. And you know, dou F by dou N TV, it's nothing but mu. Dou F by, yes, mu, dou F by dou N TV is equal to mu 3c, okay, yes. So here I should have called this one as some 4 and this one as some 5, okay. So this is nothing but equal to minus dou mu by dou V, okay, keeping T and N as constant. So dou P by dou N, keeping T and V constant, that will be equal to minus of this particular thing. So this is my equation number 6. So here we can have equation 4, 5 and 6 are also the Maxwell's relations in Helmholtz representation. You can try out if you can get more. Okay, so these are 3 Maxwell relationships. So similarly, we can, as I told you, that in each representation of thermodynamics, we can obtain a set of Maxwell relations. So we can just now do the same thing with the other representation, that is Gibbs representation. The Gibbs representation. Similarly, in Gibbs representation, I will just start with 1. You can obtain the remaining. Gibbs representation, you can get okay, 3 such relationships. That is G equal to, how do you begin with? You start with the definition of thermodynamic potential G. G is equal to U minus Ts plus PV. You can have several ways of defining it. So you take therefore what is dG equal to, therefore dG is equal to du minus TdS minus SDT plus PdV plus VdP. That is the thing. Okay. Now this du can be expanded in terms of first law of thermodynamics. That is what? Du is nothing but TdS minus PdV plus mu dN. So I have substituted for this du using this first law of thermodynamics minus TdS, whatever equations are there, minus SDT plus PdV plus VdP will be the relation. So number of terms are getting cancelled out. So this TdS of course will be getting minus TdS, minus PdV will be getting cancelled, plus PdV. So what you're remaining with is only 3 terms. I'm putting in an order, minus SDT plus VdP then plus mu dN. So that is what is remaining. So let me say that this is my equation number 1 and this is my equation number 2, which gives you the differential change in the Gibbs free energy of the system, right? From that you can define the S, V and mu in terms of G. For that you have to retain only those terms and make the remaining 2 terms as what? 0. So in order to define S, I have to make second and third term as 0. So for that you make dP equal to 0 and dN equal to 0. And how come that? You maintain pressure as constant and number of particles constant, and you allow only the temperature to vary. So in that case, you will get S is equal to minus, so that is a place where you are going to partial derivative, minus dou G by dou T, minus dou G by dou T, keeping what and what constant. So pressure and the number of particles should be kept as a constant, right? So you get one relation. Let me say A, this is my A, right? The same manner you will be getting what else? You'll be getting V is equal to simply dou G with respect to dou P, keeping T and N as constant. So that is my second equation, and you'll be getting mu equal to third one, dou G with respect to dou N. This equation already we have seen, mu equal dou G by dou N, and we define chemical potential as the Gibbs free energy per number of particles. Okay, keeping what all things, the pressure and the temperature as constants, right? So let me say that this is my C. So we have obtained the relationships, or we can say that, or I can say that S can be expressed as a function of T, P and N through G, T, P, N. Then V also can be written in terms of T, P, N. So these are known as natural variables of that quantity in the representation, and mu can be written or expressed as a function of T, P, N. If you are able to do this one, then they serve us, okay, they serve us the equation of state in that particular representation. Okay, so they these three quantities can serve as the equation of state, means it can tell you something about the equilibrium of the system under consideration. Now let's consider now let's consider certain derivatives. That is, I'm considering dou S by dou P, dou S by dou P, okay, keeping T and N constant, T and N constant. So what will be dou S by dou P? So you can do dou by dou P of, yeah, let me use the square bracket, dou by dou P of, what is S? S is equal to minus dou G by dou T, right? So it is what? Minus dou G by dou T Pn, and this dou by dou P is taken with a Tn, so I'm putting it as there. So which is equal to, I'm inverting the thing, so it's, I'm taking minus sign outside, so then dou by dou T of, what is that? Dou G with respect to dou P, Tn, so that T on En also will be taken inside, then I have to take Pn out, and what is that? Minus, what is dou G by dou P? Tn, dou G by dou P, Tn is nothing but V, so you'll be getting that is equal to minus dou V by dou T, keeping Pn as constant. So that's one of the thermodynamic, Maxwell's relationship that we have got. That is, you can rewrite this one, dou S by dou P, keeping T and N, that will be equal to minus dou V by dou T, keeping P and N constant. So this is our first Maxwell relationship in the Gibbs free energy representation. The same manner you can just work out. Giving you the two more results. Similarly, you can just check it by yourself by the same method, same token. You can see that what is dou S by dou N, so dou S by dou N, keeping T and P as constant, dou S by dou N, see S with En, this is what I am doing. First we have taken S with P, okay, now S with En, right? We don't take S with T because T and S are conjugate variables. Okay, so Ts will be always just the energy variable. So we'll be taking only P and En, right? So dou S by dou N with Tp, that would be equal to minus, you can even predict what will be coming on the other side, minus dou mu, because whenever it is N here, cross multiplication should be mu with N, T with S. This is what you have, you can always check it, P with V, already I mentioned in the previous video yesterday that in the Maxwell relation, always a cross multiplication should be involving conjugate variables whose dimensions will be same as that of energy. Okay, so when it is dou s by dou n, you have written dou s by dou n, then you can automatically understand that, okay, apart from the negatives or plus signs, it will be dou mu, because n in the denominator means on the opposite side there should be mu in the numerator, so that it is mu n pair ups on cross multiplying. So if it is s here, then what should be here? It should be t here. So dou mu by dou t with the p n, you know, okay, the other variables, mu, it is p, you know, just t and en. You can see mu is the natural variables are t, p, n. So, and please see that you get this equation in the same manner by taking the order of differentiation. You just invert the order of differentiation and try to get this one. Similarly, one more thing I'm going to write, that is involving the chemical potential, that is dou v from here I'm taking dou v with respect to dou n, dou v with respect to dou n, dou v with respect to en we are taking. Okay, so that would be equal to dou v with respect to dou n means we are keeping t and p as constant, so that would be equal to simply what will be on the other side, as you can make a prediction by yourself now. So if it is n here, on the numerator should be mu, you know, and if it is v here, the denominator should be equal to p, so that you get dou pv and mu n on cross multiplying, and you know what should come out here, it should be nothing but t and n as constant. So these three, okay, I can name, this is one, you say that this is x, this one is y, and this one say this is z. These three forms what is known as what, the three Maxwell relationships in Gibbs representation. Okay, so means you can use all the different representations. Okay, you can use the entropy representation, you can use what, the energy representation, Gibbs representation, or enthalpy representation. From each of this representation, you will be getting what, okay, a set of Maxwell relationships, and all these serve as useful relations in one context or the other. Okay, they are all applicable, but in different situations, and depending on the variety of thermodynamic situations we are going to deal with in a particular problem, you have to choose proper potential and proper thermodynamic, okay, Gibbs Maxwell's relationships. അപ്പോൾ നമ്മുടെ കൺക്ലൂഷൻ ഇതാണ്, നമുക്ക് പൊട്ടൻഷ്യലുകളും മാക്സ്വൽ റിലേഷൻസും നമ്മൾ പഠിക്കുന്ന സിസ്റ്റം ഏതൊരു കണ്ടീഷനിലൂടെയാണോ കടന്നു പോകുന്നത്, ആ കടന്നു പോകുന്ന കണ്ടീഷന് അനുരൂപമായ സ്യൂട്ടബിൾ ആയിട്ടുള്ള പൊട്ടൻഷ്യലുകളെ നമ്മൾ ഡിപ്പെൻഡ് ചെയ്യുകയും അതിന് അനുയോജ്യമായിട്ടുള്ള മാക്സ്വെൽസ് റിലേഷൻസ് വേണ്ട വിധേന ഉപയോഗിക്കുകയും ചെയ്യേണ്ടി വരും. ആൻഡ് വി വിൽ ഹാവ് ample opportunities to apply different thermodynamic potentials as well as what, the connected or related Maxwell relations in the coming topics of statistical mechanics. Okay, so I think that's enough for the first module, which was just giving you an overview of classical thermodynamics, and where we have reviewed revised our basic concepts of potentials and all other system properties. I hope that it will make our journey into statistical mechanics a bit more comfortable, in the days to come. So thank you. Make your own notes and prepare for your own university requirements as well. Thank you.